All right, it's two after the hour, so we'll go ahead and get started. Thank you everyone for joining us today at our Bird Bites seminar series. Just a couple of housekeeping items. First off, I want to let you know that we are recording this session. And second, I would like to ask if you have any questions for our speaker today, that you please save them for the end, unless they are any burning clarifying questions. So it is my great pleasure today to introduce our speaker, Dr. Larry Gould. Dr. Gould is a distinguished scientist at Merck Research Laboratories, and he's recognized as an expert in biopharmaceutical statistics, including Bayesian methods to improve effectiveness of the drug development process, adaptive trial design, evaluation of safety data from clinical trials, application of methods of data mining, and application of decision science methods to drug development strategy. And due to his outstanding contributions to statistical science, Dr. Gould was awarded American Statistical Association Fellow in 1988 and has since continued leadership positions, including the ASA Biopharmaceutical section within ENAR, and he served as editor of the Journal of Biopharmaceutical Statistics. So please join me in welcoming Dr. Gould, and I will turn it right over to you.
Okay, so I will start by sharing the screen. Do we see it?
Yes, we do.
Oh, fantastic. Okay, so let's start from the top here. So, thank you all for joining. What I'm going to talk about is actually two topics, but they're related to each other. The first topic has to do with how do you balance dose selection of doses when you, nope, yep, that's the title. There's two parts. So we'll start with the first part, which is how do you actually evaluate dose response? Now, there's a couple of ways to do this. But basically, you have to do this no matter what before you undertake the drug development process. So here's the first part. Now, in case you want to follow up on this in more detail than I'm going to give in the presentation, there is a literature reference. This is published material, and you are welcome to look at that. There's actually software available for this, and if you're interested in getting the R code that does the calculations, drop me a line because the R code that's associated with the journal article is old. Anyway, start with the introduction. So what's the objective of a dose response trial? Well, you want to find a dose to carry forward. If it's too small a dose, your trial will fail at phase 3, which is very expensive. You don't want to do it. If your trial is too big, you're going to waste a lot of time and money. So the key issues to address are, first of all, is in fact response related to doses at all? I mean, if it's not, then you stop right there. But if it is related to dose, then what doses should you carry forward in further development when you're going to be spending a lot of money and a lot of effort on evaluating the product? Now, there are other issues, of course, which doses produce responses that differ from the control. That depends on your trial design and may or may not be what you are interested in. But of course, it's useful to know that too. And the other thing, although from the standpoint of evaluating, finding which is the most effective dose, you'd be interested in knowing what the formula dose response relationship is. But this is we're talking about a mixture model here, and although that may be interesting from the standpoint of developing the pharmacokinetic models and such, it's not essential for this particular point. There is a very large literature on dose response relationships, and this focuses on modeling or multiple comparisons. This is different. So I'm not going to go into the literature, and there's just not enough time. So here, let's start with this. Here is some data from a publication by Steven Ruberg, and he fit a selection of models and found that Emax gave the best fit. And here's what the dots of the observed means are, and here's what you see dose response. So this very much looks like an Emax model, which is your typical S-shaped curve. But if you try to fit a bunch of little models here, you find out, well, it doesn't do very well for linear models, nor for quadratic, or for other possibilities. Emax is nice, nothing else works. So the thing is that I'll give you more details as we go on, but in fact, any dose response modeling approach should pick this up. In other words, you're going to try to figure out what the relationship is. If you've really got an Emax relationship, S-shaped curve, you should pick it up quickly. So here's another example where the correct model is not so obvious. This was the first in-man study of the immunogenicity and safety of a vaccine in healthy adults. And the response was, how big an increase in your immune response did you get over baseline 14 days after the administration of the vaccine? Now, if you look at the plots, I mean, there's not a lot of dose points here, which is part of what happens often in these trials. But if you look at this, it looks like linear log dose and quadratic log dose and Emacs provide good fits. Well, which one should you use if you're going to go forward to trying to describe the predict your dose response? Well, the question is, well, why would you need to choose? And the question is, do you want to find the dose response? Why do you care which model? So why is this important? Well, if you had a model-based approach that you actually picked a model, your model could be wrong, could be just something in terms of really physiologically wrong. It just happens your data show you that. Now, there's something called MCP mod, which is a hypothesis testing paradigm for concluding multiple models. You determine the doses to carry forward by selecting the most promising model or by model averaging. And you use a whole bunch of things. You use nonlinear regression, parameter estimation, multiple comparisons, and asymptotic normality assumptions. And it's very popular, but in fact, it requires a lot of assumptions. What I'm going to talk about here and later on too is a Bayesian framework for carrying out multiple model analyses. It does depend on the likelihood principle, which any good statistical procedure should. It has some attractive technical properties, and most importantly, it addresses important issues. So let's model weighting and Bayesian methods. There's a real literature on this and many examples. And again, this is cited in the paper. So onward. So here's the method. First step is to identify some candidate dose response models. That's step 2. We'll fit each model to the observed data using conventional Markov chain Monte Carlo calculations, which you can do in what Stan is really MCMC. Stan is Hamiltonian type things. But at any rate, you observe conventional Bayesian calculations. You can use Stan, you can use JAGS. You probably shouldn't be using OpenBugs or WinBugs anymore because they're not supported. And what you do is you get realizations from the posterior distributions of the parameters for each model. Now, why is this useful? Well, you can have any kind of observations. They can be discrete, or they can be continuous, they can be categorical. You can use any probability model. Data don't have to be normal. They can be binomial, Poisson, whatever. All you require is that the expected outcome for a dose is a function relating the response to the dose and possibly to some covariates and stratifying factors. Step 3, you'll get posterior distributions of the functions of parameters using the part 1 stuff. Here's the thing. Once you've got realizations from the posterior distributions of the parameters, you also get realizations from the posterior distributions of any function of the parameters. And that's important because that's where you get the stuff you really care about. So that you have the expected and predicted responses at any selection of doses, and you have the doses corresponding. And this is the other thing you really want. What are the doses corresponding to a specified target response? Now, here's a little look how the post-processing goes. You have realizations from a joint posterior parameter. These are the parameters. You then look at the posterior distributions of functions of the parameters. You get expected responses at various doses. You get the likelihood for observed outcomes. These are posterior model weights. And you get the weights to calculate Bayesian averages, Bayes averages of model-specific quantities. This is the whole point here. And what you get is an array with all of the things you care about, which are the joint posterior distributions of the functions of the parameters. It's a big matrix, but it contains everything that you need. Okay, back to where we were. So here are what is the commonly used models? Well, you could have a linear model. Now this is D is the dose and B is the parameters, vector parameters. Linear, quadratic, linear in log dose, quadratic in log dose, Emacs is sigmoid, and that's the general sigmoid there. You could have a simplified sigmoid by simply taking B4 equal to 1. It's called a Hill model. And then you have an exponential model of this sort. Many other models are possible. You could use cubic splines, fractional polynomials, and so on. They require more parameters. the value of what we have here is that it doesn't require a lot of parameters and yet provides a reasonable fit to the data. So here we go. Now, could you use more than 6 models? Yes, you could, but you may not need that, and fewer than 6 models may not be enough. This idea has been explored in other contexts, but what happens is you wind up having more models, but some of them are repetitions of the same thing. For example, a logistic model and a sigmoid and an Emacs model are fundamentally the same thing. You don't need both, just one. So how do you determine the prior weights? I mean, you're doing some posterior stuff. How do you determine the prior weights? Well, the clinicians could provide explicit weights directly, and that's what MCP mod requires. Or you can do something a little clever here and say, well, why don't you ask the clinicians to provide pairwise ratings of their relative preferences for the models? For example, do you think linear is better or Emacs is better? Do you think it's a lot better or not? You can conduct a pairwise preference matrix and you can get weights of the eigenvector corresponding to the positive eigenvalue. There's something called the analytic hierarchy procedure that uses this method. Here's an example. You have pairwise comparisons of the models and you look at the components. So for example, if in this particular, say, linear model is certainly relatively important, the same as the in any context, the same as a linear model. But a quadratic model in the context may be more important than a linear model, maybe equally important to the others. Log linear, likewise, and so on. Exponential may be highly preferred to most models, and Emacs may be as well. And so when you do all of this, what you get is model weights. I will leave aside the calculation of this. It's straightforward. But at any rate, what you find is that you 5% weight for linear, 9% for quadratic, 7% for log linear, 11% for log quadratic, 48% for Emacs, and 20% for exponential. And that's the prior weights that you would get from the for your various models. Okay, but the thing is that another way of doing this, of course, may be you can assume uniform model weights. You say, well, we don't have any preference. We'll give them all weight 1/6. Well, you could, but a better way to do this is to assume, first of all, that equal weights and then adjust the weights to reflect correlations among the predictions provided by each model. This is a little different application and implementation of that idea. This is the default, but you can specify, if you don't like any of these, specify the weights however you like. So how do we identify appropriate doses? Well, there's 2 ways to proceed, and they address different questions. First one might ask is, what is the smallest dose that provides a sufficiently high probability of an adequate response? Okay, that's the lower upper quantile of the posterior distribution of responses given doses. But you might ask to say, well, we sort of say, well, we have a response that we are interested in getting. What can we say about the doses that will give us that response based on the model? And this is all straightforward from the calculations. So here's first example: sigmoid dose response, which I showed you before. Prior weights, it turns out, by however you do this, are very heavily weighted. Well, linear, quadratic, log linear, and Emacs look most important. Okay, but you look at the posterior weights. This is an Emacs model, no question about it. And of course, the method picks this right up. And these are the correct posterior weights regardless of the prior. I could have used other priors, could have used a uniform prior, would have come to the same thing, because this is very obviously an Emacs model. And of course, you saw these before, and it's clear that the Emacs model provides the best fit to the data. Actually, let's see what we have down here. Here's the article from the data: prior weights, posterior weights. And here's the summary statistics, by the way. We wanted to figure how should we look at the distribution of the observations here. It turns out you don't need to require these to be normally distributed. In fact, it turns out that the best approximation to the distribution of the response around each dose is actually a t-distribution with 3 degrees of freedom. In other words, it's a very heavy tail distribution, not really normal at all. Well, back to here. Okay, so here we've got that. And we can look can we say, will this tell us anything about whether the product works at all, whether there's any dose response? Well, one of the things you can get out of this is you can calculate the posterior distribution of the first derivatives of your response function. And if the first derivatives are, and by the way, this is with error bars, so if the first derivative bound is lower bound is greater than 0, you have a positive dose response relationship. And that's basically a very straightforward answer to a very important question. Okay, we want to find a target dose. Well, here's the dose. Suppose we want to find the mean responses here, and we're looking at a mean response of 60. Here's the CDF of the distribution of responses relative to dose. Here's your range of doses that works for this purpose. Posterior CDFs of the dose as a function of the outcome target. So here's the actual expected response, and here's the dose difference. Differences you're looking for. Here's the range of doses that gives you the difference you're looking for. Okay, which turns out to be 20. Here's the range of doses that gives you the response you're looking for, which should be 60. And then you've got a range of doses, so that when you come to go forward with planning future trials, you're not fixed on one dose. You've got a good idea about what the range of doses is. So here we go, same thing that you just saw. So what does this mean? Well, it means that lower doses are unlikely to give you a good response, and higher doses may present an elevated adverse event risk. I'll get to this in the second part. And you do the same calculation for the AE risk. So suppose there's multiple adequate models. I mean, here's the safe immunogenicity. Prior weights are this, and it looks like they're essentially uniform. What is the posterior weights? Well, posterior weights tells you a little bit more. Posterior weights tells you that the log linear, the log quadratic, and the Emax are good fits, but there's nothing to tell you that you prefer any one or the other. And in fact, the optimal weighted Bayes dose response curve is the best fit. There you are. So what are the probabilities of doses on target dose? Here's the expected response, depending upon what the distribution is, difference from the 0 dose. If your objective is a 1.4-fold difference from the 0 dose, it's telling you that your modal dose is going to be around 40, regardless of how you do it. And your credible interval is 22 to 72. This gives you the posterior variability of responses to a 0 dose. It takes that into account. Example 3, binary responses with random center effects. Well, you can add random effects in this too. Trial in 3 centers, including, well, you can read that. And the response is a 50% reduction in seizure frequency from baseline. Now, there's Olson and Racine used non-parametric monotone regression for the analysis, and here's a summary of the data. There's wider bounds of the response probability with a random center effect. There's no center effect, random center effect, and you can see that the bounds are wider. Not a lot wider, but certainly wider. And that's fine because there's variation amongst centers. If you look at the distribution of the dose response curves, you can see that different models fit, they fit about the same. But if you add the variability from the random center effect, it's greater. And that's exactly what you should be seeing. That's good guidance going forward because there's variability here that has to be taken into account. If you average the models using Bayesian averaging, if you don't take into a center account, you get this nice tight bound. And by the way, and if you do take Bayesian center effects into account, you get these much wider bounds. That's fine, but it's accurate. And that's the point. So first derivatives, is there a dose response relationship? Well, if there's no center effect, on average, there certainly is, although below 400, there certainly appears to be below 400 milligrams, but apparently not after, which means what? What it means is that basically you've flattened the curve itself. It's you're okay going up to 400. No point in going beyond 400. So which dose should you pursue? Well, if the target response rates are 3, 3.5, and 4, and this is the CDFs. If there's no center effects, then it looks like 200 milligrams is likely to produce a response. Anything over 200 will be response greater than 30%. Okay. If you include the center effects, it's different. It's actually shifted somewhat to the right, so that the chance of a 30% response rate with 200 milligrams is really no more than about 50%. And here it was about, you know, it was about 50. The median 200 milligrams. Yeah, there's more variability in this particular, more uncertainty. Anyway, summary and comments. This is by way of introducing the idea of Bayesian model averaging for inferences about response at each dose level. The separate objectives, of course, you can determine if there exists a dose-response relationship, and you can identify appropriate dose ranges. This is all automatic. You don't have to do it. I mean, this is just an immediate consequence of the calculations. And more to the point, you get all of this stuff graphically, which is very useful for being able to communicate with people. The lower quantile gives you the dose-response relationship. You can establish or rule out proof of concept with modest trials. And the predictive distributions of future responses tell you something about what's likely to happen in the future trials. What are the advantages? Well, for one thing, you don't have to make any approximation or assumption of asymptotic behavior. You use the actual likelihood that you have every reason to believe your data provide you. You can include as many models as makes sense. You can include more than 6, although this seems little reason to do so. And the posterior distributions of doses corresponding to target outcomes can be used to determine the doses to carry forward. So maybe identifying doses differing from control may be the best dose finding strategy. At least that's commonly what people believe. But really, perhaps it's better to quantify the anticipated responses to a set of doses and use the results to determine the dose range that gives you your target outcome. You're not necessarily interested in finding out who differs significantly from control, because that may be an artifact of your sample size. But what you really want to do is, the clinically meaningful thing to do is to say, well, here's the response we're looking for. What dose gets you there? And the depends on the target responses, which depends upon a lot of things. You see, in reality, of course, effectiveness is what's important, toxicity potential, but then you have to make it something that people will actually use, the market will support. So it has to be a convenient or appealing dosage regimen. Having to take a drug 6 times a day is not a particularly appealing dosage regimen. Competition. What else is out there? What are you competing with? Because ordinarily, in many cases, there's many different very small variations in molecules that have the same mechanism of action. And the question is, what represents the more appealing possibilities? And of course, what is the cost to produce this stuff? If it's a very expensive product to produce, it may not be commercially viable or attractive. So that was the first part. That was kind of like, here's the methodology. Now, what do you do with it that might be useful? So we're going to integrate efficacy and toxicity because that's what you want to do. And again, this is there's a published article on this, and it's readily available. So where do we start with? Well, if you do not have adequate efficacy or the product is too toxic, you're going to have late stage failure. Now, in reality, you do not want to have late stage failure. Late stage failure is expensive. And so if you're going to fail, one of the executives at Merck said many years ago, the objective here was to design the trial so you fail early and often. Well, you don't necessarily want to fail often, but if you're going to fail early. That's when it's not expensive. So what does success mean? Well, you find a correct dose that balances efficacy and safety. If it's too high, you have tolerability problems. If it's too low, yeah, it's going to be safe, but it isn't going to work. So how do you find the correct doses? What models do you use? By the way, efficacy and safety dose response models are unknown and can differ. Efficacy may be measured, the quantity that's measured, to reduction in blood pressure, reduction in serum lipids. Safety responses can be discrete. Did you have an AE? How likely was it for people to have serious adverse events? So the question that we are faced with here is, how do we incorporate both safety and efficacy responses to provide guidance on dose selection, and to do it in a way that communicates the idea readily to the people who have to make use of this information? I can't stress this really too much. If you're in an applied situation, and yes, I'm in an applied situation, you have people who are going to make use of the things you do. You have to make it useful for them. Okay, there is a modest literature on how to do this, by the way. I'm not going to go into it very much, that invoke copulas or MCP mod. Okay, so here's the basic idea. Okay, and this is the key picture. Let's spend a little time looking at this. First of all, as we pointed out in the in the preceding part of this presentation, you can have a response-dose relationship. So here's a model relating response to dose. And this is, again, a mixture model, so we've got that. More to the point, we also got constant confidence interval, constant bounds about this, which means that at any dose, this is the confidence interval for the expected efficacy response. So if you have a minimal acceptable efficacy, in this particular case, 2.5, it's quite arbitrary, then you want to be sure that whatever your response you're going to get, the lower bound is at least 2.5, and the upper bound is good, but the lower bound is 2.5. So here you are, you drop this down, here's your lower dose, minimal effective dose. Okay. And this what's acceptable depends on the clinical considerations. This is not one size fits all. And now you look at toxicity and you say the same question. Here is the relationship between dose and the occurrence of an adverse event. This is the toxicity rate. And let's say the maximum you're willing to tolerate is 25%. Okay, which means that the upper bound on that curve, on that relationship, has to be no more than 25%. So you're looking at anything below here. Okay, this is below here it's fine, but above here it's not. So here's the maximum tolerated dose that's here. And here is your acceptable dose range. And you have one picture that gives it to you immediately. It is easy to read. Now, the dose response range here represents a more or less optimal, or more, perhaps one should say, acceptable efficacy toxicity trade-off. If these particular values are not acceptable, you just put them wherever they are. Okay. And there's, of course, depends upon what you mean by optimal, but this gives you a really interesting way to be able to express what's important. And again, these things are what these values here and here, although this is coincidental that they happen to be this way, that's not necessarily what's going to happen in practice. We could say that the maximum tolerable toxicity would be 10%, in which your dose is going to be somewhere around here, very, very narrow range. At any rate, it depends upon clinical considerations, and this is where the clinical input becomes very important. And you can have a conversation with the clinical folks. By the way, I say clinical because that's the environment in which I work. If you're doing this in any other environment, you're talking about the people who are going to make use of this information, and they certainly have input in what constitutes the appropriate criteria. How do you do this operationally? Okay, here's a little literature search. Well, you could use MCP mod, fitted best model, fit joint model using GLM, find significant models, and use a bivariate model. That's a way of doing it. They could compare GLM and Gaussian copula models for continuous efficacy. That's one way to do it. Oh, and the other thing here is people like to use copulas. I'll get to that in a second. Copulas copulas just briefly are a way to combine information from different distributions that incorporates correlation or association. Obvious one that we do with this, and you're familiar with this, is multivariate normal. But if if they're marginally not normal, you have to have some other way of doing it, and copulas provide a way to do it. So this is the number of ways people provided variations. Use logistic model and found the copula model was very nice. Copula models are fine, but the problem is in reality, you don't know exactly how you're supposed to do it. So here's a different approach. First of all, what are the strategic considerations? If you didn't have toxicity information, then of course your decision about doses would be related totally on efficacy. So if there's an effective dose efficacy dose relationship, then without knowledge of toxicity, the relationship doesn't change when you suddenly know toxicity. You can say you did the you did the experiment, you got both bits of information, but the dog ate the homework in terms of toxicity, so all you have is efficacy. So you still have dose response information for efficacy, and that's enough. But you need enough data to characterize efficacy. Toxicity information really narrows the dosage range. It doesn't change the efficacy-dose relationship. Now, dose response models or copulants certainly lead to complex computations. And I'll show you what happens with that. Alternatively, what we can use, and again, the reason is that the marginal relationships are important. We can use the BMA mod, the Bayesian model averaging approach to find efficacy and toxicity separately and use that to find the appropriate dose range. And we can do more than this. We can ask our folks, our clients, clinicians, say, well, why don't you tell us what constitute combinations of efficacy and safety that are important to you, and let's see if we can look upon how the likelihood of acceptable categories arises. We do that too. So we have a suite. How do we do this? Well, a little review of BMA mod, possible functional forms, get realizations from the posterior distributions of the parameters, predict responses to doses, use the weighted average of the predicted responses. The weights are based on the model log likelihoods, and the resulting predictions are almost as good as if you knew the true dose response relationship, which in fact you never do. This also allows flexible response distributions. You can incorporate random effects, stratification, covariates, very handy. And you can use existing software with essentially no extra coding. Very attractive. Here's a simulation example. And by the way, a little bit about copulas. Copula is a CDF over the unit square with the uniform marginals. And there's different ways of doing this. And what you do is that so here are some associations. If they're Gaussian with no correlation, your uniform, it's even coverage. If you happen to have Gaussian, bivariate Gaussian, and these are still uniform, but the points you're generating look like this. That's an ellipse as you expect for a normal distribution. But you have some others that are a little queer. This is something called a Clayton one, which is sort of like a horn facing to the, going from bottom left to upper right. There's something called a Frank, which is a band. There's a Gumbel, which is kind of like a Gaussian, but not quite. And then there's a Joe, which goes in the other way from Clayton. These are different association patterns. Okay, back to here. So how are we going to do the simulation here? Well, let's simulate using these different ideas. So how do we do this? We draw a value from the unit square, because what I'm going to do is simulate data and then show you how the analyses work when you just ignore how the process was that generated data, because you never do really know that in practice. So you're going to generate kinds of data and see what happens when you actually try to analyze it. So you draw some unit square values, and here's how you just do the inverse normal transform in this particular case for the continuous values, and you use the inverse Bernoulli transform for the safety. Now notice here, what I've done here is that I have two kinds of outcomes. One is measured continuous, the other is categorical, actually 0, 1. And I can actually incorporate the correlation and association between them because they, and by the way, these are incorporating between them without having to get too crazy. Without having to get too complicated. The copula formulation provides a way to do this. It's fairly convenient. Notice here there are two possible different dose-response function relationships. Okay, now it's okay to generate the data because the model and copula are known. But if the model and copula are unknown, which of course is always what happens, it's not okay for analysis. So what we're going to do, we're going to apply the BMA mod to each response sequence and use a graphical representation to identify useful dosage range, like the picture that I just showed you. And the question then becomes, well, that's fine. Does the choice of copula or response functions matter? Well, does it, are we okay to do this? Expressing non-independence, we could, well, this is a way of expressing non-independence here. We could fix a particular kind of copula. We could assume that this is a pair of model-specific CDFs. In other words, if you really wanted to go with the copula route to do the analysis, you have this. You have estimates of model and copula parameters to predict responses to new doses. This is computationally challenging. You got a whole lot of parameters all of a sudden. And you have you can use generalized mixed models, non-parametric Gaussian process. This is ways of expressing non-independence of efficacy and toxicity. For purposes of simulation, copulas are good. For purposes of analysis, not so good because it's complicated. And all of these assume a known dose response function and a known copula. But if you don't know either, then you're going to get a problem. Okay, back to here. So let's move on. So dose response, here's the simulated antihypertensive trial illustrated. So the efficacy is actually an Emax model, and the safety is actually a measured thing. It's an exponential model. Okay. Toxicity is, efficacy is this is the relationship, by the way, between dose and response. Okay, so this is exponential. The probability of the likelihood of an adverse event increases exponentially with dose. So efficacy is change in sitting diastolic blood pressure from baseline, and here are some the parameter values. This is obtained from the literature. Toxicity is the presence or absence of an adverse event, and we're going to say that we're relate this with a logit, and this is a Bernoulli now distribution. And these are the parameters. We are now going to analyze the data ignoring the generating process. One of the other things we can do is define some clinically interesting categories. And so, for example, so if you have a diastolic blood pressure reduction between 5 and 10 millimeters of mercury, and you don't have any adverse events, that's really the best outcome. If you have, if you don't have severe adverse events, but the blood pressure reduction is good, that's fine. If you have a small reduction in blood pressure, but no big deal with adverse events, that's not great. And if you have a severe adverse events toxicity, that's not acceptable at all. So these are the four categories. This is best, this is good, minimal, and this is worst. And so here, how do we do this? Well, first of all, we're going to use the copulas only to generate the data. So we are going to generate actual observations using 4 copulas. We'll generate a UV sample from the copula. We'll generate the outcomes, and then we'll generate categorical values, which are a function of these 2 outcomes. And we have 4 different copulas that we're going to try this with. This is a simulation exercise. The category analysis, we will interpret these as adverse event severities. So the observed severity value is a beta distribution with this value, and these are the adverse event severity categories. This is how we're defining things. Okay. And we'll use BMA mod marginally for efficacy and safety, and we're going to ignore the actual copula and model that generated the data. Back up. Adverse event severities are essentially, this is how we're going to simulate them. They have a certain probability of occurrence, and we could simply say, once you get a severity value, which is going to be a number between 0 and 1, we'll categorize this at none if that value is less than 0.5, moderate if it's between 0.5 and 25, 1.25, and severe if it's greater than 25. That's just the rule for generating the value category assignment. Okay, here's the simulation results. Okay, Now this is the response, and this is the difference in response. So the degree of blood pressure lowering relative to to control. So here's the efficacy, and here's the safety. We have a small tolerance of about 25% for severity. We don't want it to be severe, and we have at least this amounts by 0.5 or so for efficacy. And you can see that these are very well separated. So for the Gaussian copula, these are generated the data. We do the analysis. Do the analysis exactly the same way. This is the range it tells you to use, somewhere between 62 and 70%, 0.62 and 0.7. Here it's very similar, somewhat wider for a Gaussian copula with high correlation. Clayton copula, very similar. And Joe copula, very much like the Gaussian copula with rho equals 0. So the heavy bars, these identify, back up, not there yet. These heavy bars identify the dose ranges that are acceptable. Okay, next. Well, what happens if you use categorical data? Well, we've got desirable dose ranges. So let's say we're going to combine a best, and then this is the distribution of probability of being in the best category as a function of dose, best plus good as a function of dose, minimal plus worst, and worst. Now, let's get the same thing for all of the pictures. This is very interesting. What it says is that, first of all, the dosage ranges are very nearly the same, regardless of which copula model you use, and that this is the range of doses that you could be considering if you want to be in the situation where you have an acceptable degree of effect, good plus, good plus at least good plus best. Likewise here, and you're not in the range of worst. Worst is controlled. Minimal plus worst is fairly low, but in fact it dips down below here, and it's similar here. But the thing is, if you're looking at best plus good, this is where you want to be, and this is the dosage range. Everything else is pretty much constant in that dose range, more or less, although certainly not outrageous, depending on the copula. So the desirable dosage ranges are wider than the marginal ranges, but they're defined by different criteria. Okay, here we are. Okay, so previous slide shows how category distributions vary with dose. If we're talking about a difference from dose, we need a definition for categorical outcomes. Okay. Now, how do we do this? Well, there's something called Hellinger distance. That's kind of like a Euclidean distance, but it has certain advantages. And the nice thing about the Hellinger distance, you're asking yourself it's a multivariate way of looking at distances. And if you look at it that way, you see, for example, if depending upon the copula, it really does matter. But the thing that's pretty consistent here, regardless of the copula, is that the distance from the zero dose really is great within this range, greatest in this range, and it's pretty much true for no matter what copula you're looking at. And this is due to the fact because that in this range you are actually getting better efficacy. But here you see the distances increasing when you go off to the right. And why do you see this? You see this because this is driven by toxicity. So it seems that the association correlation does seem to matter, but only in terms of magnitude. In terms of the guidance you're given for the dose, it doesn't matter, which suggests that in fact, unless there's extreme correlation, the marginal approach using BMA mod works pretty well. Okay, here's an actual trial. This was a trial in which they had 3 doses of something called lubiprostone for the treatment of constipation with and without irritable bowel syndrome. IBS is a real problem here, and you want to sort of, well, constipation is a problem too, but we won't get there. At any rate, so here's what was found in the published article. They had four doses, 16, 0, 16, 32, and 48 micrograms, approximately the same number of patients at each. Here was the mean change in satisfactory bowel movements change. So then that did increase. The bigger the dose, the better the result here. Number with no relief, with relief, that increased as well. And the number, but so did the number with an adverse event. So how do you do this? Well, look here. What we've done here is done bivariate plot, simple, kind of plot. Here's the response that we're looking at. Here's the event. Here's the contour of 95% for 16 micrograms based upon the predicted observation. 24 micrograms, 32, 40, and 48. Keep in mind, we didn't have 24 and we didn't have 40. These are predictions based upon the model fit. And likewise, we have the proportions with satisfactory relief in this way with the model related, dose related relationship. So what did we find out? Remember, we had changes from, this is satisfactory relief. If you are having irritable bowel syndrome, that's not satisfactory relief. Anyway, here's what we got. The definitions of minimal clinical response and maximum tolerable dose define the dose range. The original article compared the various doses against placebo with multiplicity adjustments, and they found only that the 32 milligrams and 48 milligrams differed from placebo. That's 32 and 48, didn't have 40. However, 32 or more may be better, certainly gave better efficacy than 16 micrograms. And in fact, 40 micrograms, maybe even 36, would be almost effective as the 48 microgram dose. Again, you're predicting what the responses would be. You get almost as good as 48, and your response will be almost as good. Keep in mind, event here is adverse event. The 48 milligrams is huge. 32, you're getting close. 40, you're certainly getting close in terms of the overlap. And you have a much lower liability for adverse events. So what are the key conclusions here? Well, first of all, the approach is based on Bayesian model averaging. So our aim is to predict responses as functions of dose based on observations of efficacy and safety at specific doses. Here's the key thing. There is no hypothesis testing involved. There is no type 1 error involved because there really aren't any hypotheses that we are testing. It is a focus on parameter estimation in a specific mathematical model. And the key thing here is that when you understand what the response is, you can actually use that as input to thinking about how you should make decisions, because the implications of various outcomes have very real financial consequences. There is no commitment to a specific marginal dose response model, which is very good. It gives you great flexibility. If you have uncertainty in the dose response data, that translates directly to predictive variability. Key thing here is you can read minimum effective dose and maximum safe dose directly from graphical displays and numerical summaries, which from the standpoint of communicating something to clinicians or clients or the people you work with is very, very desirable. And the other thing that's important here is that the existence of a dose-response relationship, which is often what hypothesis testing is determined separately from the identification of the doses to carry forward. This is a real distinction that often is missed. And the fact that you can have the first derivative of the predicted response relationships actually gives you the existence of the dose response relationship very immediately, and in fact also tells you where you're likely to have it plateau and cease to be increasing. So this is a good place to stop. I like this one. Editors didn't really like this, but here's the comparison of the Bayesian and MCP mod approach. The clinical team decides on the core aspects of the trial design and specifies the number of dose response models and doses to include. So MCP mod says, well, we'll determine model-specific optimal dose response contrasts and the sample sizes needed to detect the dose response relationships. Bayes says we'll identify the likelihoods and parameters and we'll determine prior model weights. Fit the models, estimate responses, and then we have to assume asymptotic normality of parameter estimates. With Bayes, you just use MCMC, which is kind of the computational price you pay to get the realizations from joint posterior distributions of each model's parameters, get realizations of the functions of the parameters. MCPMed says you have optimal contrast to identify each model dose response relationship. So you got a lot of pairwise comparisons going on here, and you're have to there employ a multiplicity corrections. Bayes doesn't do any testing. So you include credible intervals, and you can determine the positive dose response conclusion on the posterior distribution of first derivatives. MCPMod says you estimate target doses to evaluate using inverse regression based on the best model or a weighted average of models, and you determine the precision using bootstrapping. Bayes says you determine the posterior probabilities of doses corresponding to responses falling in the specified interval. And you can, more importantly, you can use this with utility functions or other information to guide dose selection. So this is probably a good place to stop and ask if there are any questions. So please let me do that now.
Thank you very much, Dr. Gould. Any questions from the crowd? Going once. Dr. McQuarrie, I saw you went off mute.
Yeah, so when do you typically use these type of models? Are they typically done in phase 1 or phase 2, or like the transition into phase 1, phase 2?
Either one. Normally, the way things, in my particular view on this, phase 1 and phase 2 are for purposes of estimation to guide what you're going to do in phase 3, when, according to the regulations as they currently exist, you need to establish adequate evidence to support efficacy, and that usually involves hypothesis testing. So you really need to have adequate sample size. But the short answer to your question is that is actually, you would typically do that in phase 2, maybe even in late phase 1.
All right. Well, thank you very much for sharing your expertise with us today. We really appreciate it. I will now turn things over to our wonderful bird program manager, Sarah Robbins, with a couple of announcements.
Thank you again, Dr. Gould, and thank you for everyone attending our first February Bird Bites. I have put in the chat Dr. Gould's contact information, so please reach out to him at larry_gould@merck.com with any further questions on Bayesian modeling strategies. Really want to point out too that we have a second Bird Bites happening at the end of this month with Doctors Manisha Desai and Leah Welty from Stanford and Northwestern respectively on improving reproducibility of team science, a bird's eye view. Additionally, that information is now located also in the chat, but also want to highlight that we will not be having a March Bird Bites and encourage you all to attend the 2026 CCTS Annual Spring Conference with the theme of AI, Bridging Clinical Care, Innovation, Research, and Technology, which occurs Tuesday, March 31st from 8:30 a.m. to 5 p.m. at the Central Bank Center. The link for more information and registration is included in the chat. But until then, we appreciate you all joining us today, and we look forward to seeing you at our next Bird Bites. Thank you again so much, Dr. Gould, and we hope that you're having a wonderful time in sunny Florida.
Oh, thank you. Thank you for the opportunity, and wish you all best. Anybody has any questions or whatnot, just let me know. I'll be happy to respond. And if you would like the software, please let me know.
Appreciate it. Thank you. All right, Emily, turn it back to you.
Thanks, everyone. Have a great Monday.